So, first of all, thank you, Hans, very much for your very passionate invitation. I'm very happy to be here. And since my talk is not going to be concerned with signal analysis, I'm going to talk about the transition from quantum to classical mechanics, I prepare a very non-technical and very hand-waving talks, and this is why I prefer to do it on the blackboard. So, delocalization, because I will get to the point where, in some situation, I will explain the setting in a few minutes, we will need to jump a little bit on the vocabulary of Jean-Pierre a while ago. We will need to analyze objects by local objects, but to synthesize objects by very unlocalized objects. And the reason for that is can be illustrated very much with something which has nothing to do with quantum mechanics, but it's very closely related. It's a drum. Let me erase Fourier for good. Everybody knows that a drum can be modelized like this. You have a boundary here, closed. And when you excite your drum, it's like looking at the Laplacian on the drum and looking at the modes of this Laplacian. And it's very well known that if you look at these different modes, which are eigenvectors of the Laplacian, and if you go to the high values of the energy, these modes localize somewhere. For example, here, some we localized on these rays, some other we localize on other rays. I don't want to draw by chance. But if your drum is a real drum, this is going to work perfectly well. Now, if you change a little bit your drum, and you stretch it a little bit like this, it's not a drum anymore, but it has the shape of a stadium, like this. That is a piece of cylinder here and two half circles there. Then none of this drawing is valid anymore. If you look at still the mode exists, still you have a discrete set of eigenvalues, you have harmonics. But for most of the modes, when the energy goes to infinity, the modes with completely unlocalized on the total space available. That comes from the fact that the classical dynamics of this billiard will be ergodic, chaotic, but these are just words. The fact is that you have this delocalization of the wave function. These modes are going to be called wave functions in quantum mechanics. Of course, unlocalized object can be perfectly well analyzed by localized object. Wavelets have been done for that. I remember the picture of turbulence by Marie, where she sees that some energy are localized somewhere. But in this case, no success has been done to understand what is the structure of these modes by very localized objects. In fact, as far as I know, in fact, it's not only that you're delocalized, but you delocalize in a very uniform way. In fact, for high value of the energy, not only you unlocalize, but you tend to be equal to 1 everywhere. And still, you miss something. This is a theorem, actually, but you miss something in this theorem because you know that there are very, very strong structure underneath, and this structure is difficult to understand. You know that there is some structure just because you know that the spectrum is discrete. That is, you cannot do the same thing for all value of the energy. So there is something very special which works, and this thing very special is something that you don't understand very well. So since we don't understand very well, I shouldn't talk about that. But let me just mention one point more, is that when you look at the flow of these billiards, it should be something like this. That is, by billiard, I mean you have a straight line between the border, and each time you touch the border, you reflect by the Descartes law. You know that this flow is very, very sensitive to initial condition, and you know that you have always at each point. I have to be honest, I'm cheating a little bit because this should be a drawing in phase space. So I put a drawing in configuration space, but think it's a phase space. At each point, you have two directions which correspond to direction called unstable or stable manifolds, and these directions are exactly the direction on which, when you go to positive time, you will stretch like this, and if you go to negative time, you will unstretch. I mean, you will stretch, but you will stretch in this direction if you go to positive time, and you will stretch in this direction if you go to negative time. Now, this is a baby model of a local phase space, in fact, because these two manifolds, all of them have the dimension of a configuration space, and the set of two looks like just a space of time and frequency. Of course, they should be orthogonal. They are not, but you can make them orthogonal by some change of variable.
What do you mean by sketch?
Étiré.
Étiré, I know the word, but I don't understand.
Yeah, so this means this means that if you take 2 points here, as close as you want, you always can wait time long enough in such a way that will be separated by a given quantity.
Yeah, I was thinking that even if you look at the transition from the circle of the time, really becomes essential.
Exactly. In fact, if you go from this to this, these two pieces of manifold here, just they do, I don't know why, but they end up to be a circle around the point. And then you just remains on the circle and you have stability. Okay, so just to mention that because we need it later on. Okay, I'm not going to make a crash course in quantum mechanics because it's time for lunch almost. But let me show you the object I will use. No, first of all, sorry. So once again, as far as I know, there is no clear explanation of this, explaining from anything you want why this value will be a value of the energy and this value is not going to be a value of the energy. This frequency will be an harmonic and the other one not. But in quantum mechanics, there is a time energy inequality, which is a kind of Heisenberg principle, but not with P and Q, not in fact exactly with time and frequency, but with time and energy, which tell you that if you look at the spectrum of your operator, that is a set of your harmonics, and if you look it, I'm speaking with quotation mark, with a precision delta E, and if you know this is related to a certain scale of time in such a way that this has to be bigger than 1/2. What the meaning of this is sometimes not very clear, but the way I understand it and the way we can use it technically is the fact that if you know very well the quantum evolution up to a time delta t, then you know the spectrum with a precision delta E.
And you are always talking about discrete spectrum.
Absolutely. All the spectra are going to be discrete. You see, the point is that when you go to high frequency, to high value of the energy, eigenvalues accumulate. So in a certain sense, if you do average, you lose everything because you have a lot of eigenvalues. So the point is to have a precision as small as you want, and since you have this relation, you need to know the evolution for time as big as you want. So there is a clear link between precision in energy and long time evolution. And what I would like to show you is the fact that though we live in a quantum world and but we don't see the quantum effects, we are very familiar with classical mechanics, and there is something called in physics principle of correspondence and mathematics, well, several names, I don't want to mention all of them. In principle, you know that quantum mechanics is associated to a certain scale of actions. This scale is given by a number, which is a Planck constant. That Planck didn't like so much. In fact, he chose H for Hilfe in German. It was kind of Buetsauvetage. And all the formalism of quantum mechanics depends on this constant. And when you formally let this constant go to 0, you're supposed to recover classical mechanics. That is quantum mechanics. This should imply that quantum mechanics tends to classical mechanics. And in fact, sorry? Except when it doesn't, exactly. Exactly. And in fact, it doesn't. And it doesn't because precisely things has to be analyzed by localized objects and synthesized by unlocalized objects. And this is what I would like to show briefly. Let me mention that it's not only that you tend to another mechanics, it's a paradigm change. That is, you don't have space anymore. And this will be my conclusion, that in some situation, you don't take classical mechanics and you don't get a true space. You get different space, but you get a space which depends on the dynamics. So you completely abandon the Newtonian point of view, telling you that the classical mechanics live in a space which is given for granted and in which you play with things. The space will depend on the dynamics. Okay, so some formulas concerning the object I'm going to use. So I will use gabarets, coherent states. Our gabarets, as their name indicates, were invented by Schrödinger. And in 1926. Sorry? Yeah, no, that's Ingrid is not here, so let's not think about that. Okay, and this will be an object psi that will be a function in L2 of Rn, and function psi indexed by a point in phase space that I call PQ. Phase space, once again, for people who have forgot everything about dynamics, something like time frequency, it's a phase space of x. And this is exponential minus x minus q squared divided by 2, exponential I px like this. And there is a normalization, which is pi to the minus n over 4. This is not the gabarets I'm going to use, because I'm going to add, influenced by wavelets, a parameter of dilation. I will put an h bar here. So in fact, we are, let me put it here in h bar, though I'm going to drop it immediately. We have 3 parameters, 2 parameters, which is classical parameters of a phase space, and this parameter here, which is the same than here. Sorry, I don't have time to make this thing more precise, which you see indicate how localized you are. Basically, this is just a regular wavelet, a regular gabaret, with a Gaussian shape, but a Gaussian with size square root of h bar, basically. And of course, we are going to put h bar small in this kind of thing. Now, it's a nice formalism because you have a decomposition of identity. We heard about that this morning already. This
Small, you will have to be very careful.
I will be very careful. Does this answer your question? Yeah? Okay. It's the fact that if you sum of a dp dq, and here I guess you have 2 pi h bar to the n, but I'm not sure, then you get the identity. Identity in L2 over n. And this is independent of h bar. Not totally independent of h bar, because h bar is here. But it's valid for all value of h bar. Now, when you have something like this, and when you think that your classical phase space is also classical phase space is R2n, which is Rn for the impulsion and for the position. You see that on this function you can put classical observables, that is function b of p and q. And out of classical function b and p and q, you can build by almost the same formula something like this. That is, I smear out with now my function here. And what I get is not the identity anymore, but an operator B which acts on L2. This is one way of looking at quantization. And the point, the nice point about here is some that it shares actually with other things.
And the BPQ for the moment can be split together for the moment.
Yeah, it can be even horrible, which is a characteristic of generality. No? The point of this formula is that if now you look at classical setting, as I was presenting here, moving here, I can compose B by a flow and define BT of P and Q is equal to B composed with a flow P and Q. Okay. Now if I put here now a T here, I get obviously a T here. I didn't do so much. But the important fact is that, and when I use tilde, this means that it's almost true for h bar almost equal to 0 with almost every hypothesis. So I'm very vague on that, right? But it's something like,
You can make it precise.
I can make it precise, but I won't. I can make it. Okay? And the fact is that this operator now can be written as a unitary operator times B times its inverse. That is, this new operator is almost, it's something like conjugated by a unitary operator or the one you had at B equals 0. Equal T equals 0. Okay, and this is basically what we called quantum mechanics. Because in quantum mechanics, the evolution is not given by a flow. I don't even want to write the Schrödinger equation. In quantum mechanics, the flow, it's a flow, but it's not a flow in space like this, a flow in a Hilbert space. And at the same time that you have that the classical flow preserve a certain structure, which is symplectic structure, so to speak, which actually it's not simple and not hectic. And you have the same symmetry on the quantum size. You have a flow but on a Hilbert space, and the symmetry means that this flow is unitary. So this is true, can be proven, it's not even very difficult. But this is true when h bar is small. This is the meaning of this. And the other parameter is the parameter t. And in full generality, and including the chaotic one, it is true when t is smaller or equal, let me make it strictly smaller, than the logarithm of 1 over h bar times a certain constant c related to some fancy object like Lyapunov exponent and things like that.
This is now we are starting to be precise, but this is a definition.
Yeah, exactly.
Okay.
Exactly. And the point is that when you go, you see when h bar goes to 0, this log tends to infinity, but kind of slowly, by the way, but it still goes to infinity. So you might say that when t is bigger than this should be that plus some correction. No. When t go further to this threshold, everything totally blows up. This is not true anymore. that is a true quantum evolution, we have to read it in the other way, the true quantum evolution is not equal closely, I mean, it's not close to something which should be quantized by this. It's a fact. It's very easy to check, except in some very, very simple cases. Now, what to do if we have this? And this is the point of the result I'm going to present. Yeah, in 6 minutes, 7 minutes, 10 minutes. Okay, fine. Okay. It's the fact that I just take this little image and I fix to a point, I fix my, well, let's say I just see it. This manifold here, which was here, called the unstable manifold. That's the direction where it hurts, basically. Now, associated to this and to a function A in, say, Schwarzkreis, well, anything, in fact. Let's say Schwarzkreis of or D, you will build a state psi. Here is a point PQ, again. So everything will be local here. And psi of PQ indexed by A, it's not going to be this one now. Maybe I should call it phi. No, let me call it psi here, because the formula are going to be the same. And what is this? It's just I put an integral over lambda of Z, this unstable manifold. I make a superposition of wavelets, of gabarets. That is, I have a certain measure on this manifold. I just smeared exponent by psi of mu, where mu belongs to this. That is, let me draw a picture. I'm making a superposition of gabarets here with a certain density A. Should be some phase also, but I forgot it. Now you see that A can be, in fact, this is the meaning of this anything, can be extremely with small support. So I have still something which is localized in phase space around this point, because it's just a superposition of objects which are localized in this point. So it's absolutely something like this. But now if I extend A, suppose that A have a support which grows, I will get some state which will involve all this manifold. And this manifold, in most of the case we know, has a particularity that is it's not closed, it goes forever, and it's dense in this. This is more than ergodicity. It's dense here. So you see that by constructing such state like this for A very unlocalized, you construct objects which in a certain sense are very well localized because they are localized on this submanifold. But since the submanifold is dense, if you localize on a dense submanifold, you just unlocalize on the manifold where the sub is. And this is exactly the kind of object we'll have. And what we get in this case, I'm going to, is the fact that now, for t bigger than this threshold, we will get, for b of t, the true quantum evolution, which is defined forever. The true evolution will be closed to something which is very close to here. Here I just have to put an A, that is, I have to change my gabarets to something which is a little bit localized, but something which is not the Q space, or space. And here we'll get an A, which depends on Z and T. Another one, and nothing else. So this is a theorem, so to speak. The theorem tells you that you have a representation of your quantum evolution for time longer than this threshold, which a little bit looks the same, except that is exactly what I was saying at the beginning. That is, if you let this operator acting on a function, you analyze by something which is localized, because you take scalar product with this, But you sensitize with something which is totally unlocalized. And this works. Now, in the very 2 or 3 minutes I don't have time to explain what is this function here, except that AT of Z is equal to a certain operator BZ of T acting on A. And this doesn't depend on A. You see that, in fact, at the classical limits, instead of having something which was driven just by a push forward or push composition by a flow of functions, you have now something which lives on this unstable manifold. That is, the paradigm is completely different. In your phase space is another space, non-commutative, but it's a space associated to this set of unstable manifolds. So the paradigm might change, but the theorem is true now, and it works. Now, 3 little things to finish as a conclusion. So, why is it some need of this in a certain sense? Well, there is a need of this because if the world where we live was purely classical, it will be a total disaster because, for example, matter wouldn't be stable. Everything would collapse, everything would. That is the effect of chaos, which are so nice, are also some destructive part that we don't feel. So, in fact, it must be that.
I thought that Pauli saves us. That's a difference.
Sorry, Pauli?
We are saved by Pauli. We
Yeah.
will collapse without Pauli, but we are not talking about.
Yeah, well, yeah, we are saved by Paul. Yeah, let me save by Paul today.
Paul is better than Pauli. Yeah.
We have a big head. So, yeah. So in fact, this is exactly why you have traces of the non-commutative of quantum mechanics which ensure at least a new paradigm or something. I'm not sure that the other one doesn't work, but nobody knows if the other one works. That's the point. Now, and this is a musical comment. Yeah, there are two musical comments in fact. The first thing is that this representation is totally redundant, in fact. It's not at all unique. And it's redundant, that is, you use a lot of information in addition. This reminds a little bit musical notation, where you get something extremely powerful by redundancy. But the other thing, more physical, so to speak, is that this is valid. The unstable manifold will help you, the set of unstable manifolds will help you to understand what is the asymptotic when the time goes to plus infinity. And if you go to time going to minus infinity, you will have to use the other one, the stable manifold, which plays exactly the same role as the unstable, where time goes to minus infinity. So in fact, it's kind of like you break the invariance with respect to time, because you have your space now, you have 2 different paradigms if you go to plus infinity or if you to go to minus infinity. And in particular, it should be something in the middle. That is, how do you pass, for example, for t very big to t very, very big negative, t very small negative? What's happening? And it's happened just that you function, this function, at of z, or the operator, this kind of thing, which lives on these things when you go from time passing to 0 and negative, suddenly you will have to change the point of view and passing from here to here. And in fact, if you think that if you just put some screwdriver and you do that this, and you put that this is just Q and P by moving the nonlinearity, you have just things where a signal which should be in Q suddenly passes a signal of P. And this is what, if I remember the young days of wavelets, I think Jean-Claude who showed us, that is what our ear does. Because if we have low frequency, you listen the signal, and when you go close to the last key of the piano, you turn to listen a frequency, and you say it's an A. Really. It's exactly the same thing. That is, if you would do the same classically, you would done nothing. But since you have this quantum correction, I'm sorry to be so vague, then you get something which now lives on the P space. But this is some kind of Cartesian coordinate only locally here. So in fact, you have something like Fourier analysis, which is associated to this unstable or stable manifold. That is, you have a kind of delocalization which looks like Fourier, but with a lot of non-linearity. And I should stop here.